In this video I'm going to talk about Faraday's law of induction, and there is a mathematical formula to go with this. But basically the definition of Faraday's law of induction says that the induced or motional EMF equals the negative of the rate of change of magnetic flux linkage, which we can see in this formula. Epsilon equals negative n delta phi over delta t. This delta phi over delta t is the rate of change of magnetic flux, and multiplied by n gives you the rate of change of magnetic flux linkage. So let's have a look at this example. We have a bar magnet, which can be seen as like a mass, on a spring, and we displace it from the origin and we get simple harmonic motion in a sinusoidal type way. So let's just look at as the north pole approaches here we have a coil connected to a voltmeter. As the coil approaches the wire, the magnetic field will be increasing across the wire, and when the bar magnet is in the middle of the coil, there will be no magnetic field, and as it leaves the coil like this, the magnetic field will be decreasing. So what we actually observe is, or we could measure, would be a wave-like. This would be over one cycle. This would be the maximum magnetic field, then it would go down to 0, then it would go down to a minimum value, and then it would go back through 0 again and then go up to the maximum. So it would be a periodic magnetic field. Now, the Faraday's law of induction tells us that the induced EMF is the negative of the rate of change of magnetic flux density. Now, because we have a changing magnetic field, therefore we have a changing magnetic flux and therefore an induced EMF. But the rate of change of magnetic flux is another way of saying the gradient of this curve here. So if I put a tangent, if I put a ruler to the curve at a few places, here at these 3 points, the gradient is 0. We have a maximum, a minimum, and a maximum. So we have 0 induced EMF here, here, and here, if we have the same scale on the time axis. Now, if we look at this point here, the rate of change of magnetic flux is at a minimum. Therefore, since there's a negative sign here, the rate of change of EMF is going to be at a maximum. And at this point here, the rate of change of magnetic flux is going to be a maximum. Therefore, the rate of change of EMF is going to be at a minimum. So we end up seeing the curve for EMF is also a sinusoidal, but it's been shifted to the right by a quarter of a wavelength. In fact, the negative sign in this formula choose another color for that. The implication of the negative sign is from something called Lenz's law, which is a consequence of the conservation of energy.